Hello, everybody. My presentation will be about aperiodic surface mass transport observed in both GRACE and GNSS time series. But I'll start with a little bit of background about GNSS station position time series. So I assume everyone in the room knows that GNSS station position time series include linear trends with occasional discontinuities, either due to earthquakes or equipment changes. In some cases, we can also observe transient events such as post-seismic displacements or elastic rebound under current ice melting in Greenland, for instance. So far we have a list of the different components that have been accounted for in the ITRF 2014 kinematic models for GNSS station positions. But that's not the end of the story, because there are still a lot of interesting things in the residuals of the ITRF kinematic models, such as various periodic signals and also aperiodic variations, also called noise. So if we want to characterize the spectral content of those residual time series, we can look at their periodogram. We can see that this periodogram are quite noisy for a single station, but the picture gets much clearer if we compute the average periodogram of the residual time series of many stations. We can now identify a number of spectral peaks in the periodogram, which indicate the presence of periodic signals in the time series, and which can be grouped into three families. The first family of spectral peaks are at harmonics of the solar year, and indicate the presence of seasonal signals in the time series. So parts of those seasonal signals are known to be due to loading deformation of the Earth under surface pressure variations. Another small part is due to thermal deformation of the ground and the monuments, but there's still currently a significant fraction of the observed seasonal signals that remains to be precisely understood. The second family of spectral peaks are at harmonics of the GPS magnetic here. Those are not expected in station position time series, but actually result from GNSS errors, mostly orbit modeling errors, but also to a smaller extent station-specific errors such as multipass. So there's work here for the IGS to improve our orbit models and try to mitigate station-specific error sources in order to get rid of the spurious drag-magnetic signals in our station position time series. Then the third family of spectral peaks are at this triplet at periods around 14 days, which are due to some tide modeling errors, and which we hope to see reduced in the next IGS reprocessing thanks to improved sub-daily EOP tide models. Now, below all those spectral peaks, the continuous part of the spectra characterizes the aperiodic variations in the time series, or the background noise. We can see that this background noise follows quite well the behavior of flicker noise at low frequencies. And then at higher frequencies, the spectra flatten, which indicates the presence of additional white noise in the series. So the rest of this presentation will be mostly about flicker noise, so let me give some additional background. Flicker noise was identified in GNSS station position time series already 20 years ago, and it has since then remained the preferred model to describe the time-correlated noise present in GNSS station position time series. Why is it important? It's because the presence of flicker noise in the series needs to be taken into account if one wants to assess realistically the significance of any geophysical feature in the series, and in particular the significance of the station velocities. But where does it come from? Well, different possible origins have been proposed in the literature, but none has so far been positively identified which could explain the level of observed flicker noise, nor its spatial correlation. So the origin of flicker noise in GNSS time series currently remain unclear, and that's the mystery we've been trying to unveil. So we first looked at time series from other space geodetic techniques such as SLR, VLDI, and LORIS, but those turned out not to be very useful for the purpose because of the higher level of white noise mainly in those series than in GNSS time series. So we then looked at GRACE-derived time series of equivalent water height. We used different regularized GRACE solutions so that we didn't need to apply any smoothing or filtering, including 3 Mascon solutions from JPL, CSR, and GSFC, and 1 spherical harmonic solution from GRGS. We restored the atmospheric and oceanic de-aliasing products when necessary so as to compute total surface mass variations. And like we did for the GNSS station position time series previously, we computed an average periodogram of the equivalent water height time series over the whole Earth surface, accounting for the presence of periodic gaps in the GRACE time series. So here is what those average periodograms look like. We have again spectral peaks at harmonics of the solar year, which are expected from seasonal surface mass transport. Then there's this peak at 161 days, which is known to be due to the aliasing of S2 tide model errors, but which is curiously absent from the GSFC Mascon solution. But what's more interesting to us is that the average background noise of GRACE-derived equivalent water height time series seems to also follow a flicker behavior. Hence the question of whether this flicker noise comes from errors in the GRACE solutions, or if it could be real aperiodic surface mass transport signal, which could deform the Earth and maybe explain part of the flicker noise in GNSS time series. So to get an idea on this, we first look at the spatial distribution of the noise in GRACE EWH time series. We started by averaging all the different GRACE solutions over the same JPL Mascons for comparability. Then we removed the trends and periodic signals from the time series and plotted the root mean square of the residual EWH variations, that is the amplitude of the background noise in GRACE EWH time series. So the first observation that can be made about these maps is that the distribution of the noise in GRACE EWH time series nicely follows the distribution of the expected surface mass transport signal. For instance, the ice melting zones and the major hydrological basins clearly stand out with higher levels of noise, while the tropical oceans and the desertic areas clearly have less noise. The second comment is that the 4 maps look pretty much alike, although there are differences, but which are not of importance to this presentation. Next, we looked at the correlation between the noise time series from the different GRACE solutions. And it turns out that that noise in the GRACE solutions is well correlated among the different GRACE solutions, especially in areas of expected surface mass transport signal. So given the geographical distribution of the noise and the high level of correlation of the noise between different GRACE solutions, it seems quite clear that the background noise in GRACE EWH time series is actually mostly real aperiodic surface mass transport signal. So next question is how much of the flicker noise in GNSS time series can be explained by loading deformation under this aperiodic surface mass transport signal observed by GRACE. To answer it, we compared GNSS station position time series with GRACE-derived loading displacement time series. I won't go into the technical details, but directly move to some illustrations. Here's the example of the station in Poland, GNSS time series in blue, GRACE time series in red. The time series shown here include all the periodic signals which we've seen before, seasonals, draconitic, etc. But since we're interested in the background noise only, let's remove all those periodic signals and look at the residual variations. We can observe a quite nice correlation here between the GRACE and GNSS time series in vertical. There seems to be some correlation as well in horizontal, but although the GNSS time series are clearly more scattered than GRACE-derived loading displacements. The station in Poland is in an area where most of the surface mass transport is atmospheric, so let's look at another example with mostly hydrological variations. Again, we can see quite nice correlation here with the background noise in all three components, especially at inter-animal timescales. Then to get a global view of the correlations, here are maps and histograms of the correlation coefficients between the noise in GNSS time series and the noise in GRACE-derived loading displacements. The average correlation is around 0.5 in up, around 0.2 in the horizontal components. And there are also interesting geographical features in those maps, but I won't go into details here. But the picture is not as pretty if we look in terms of relative variance reduction. So here we compare the variance of the noise in raw GNSS time series to the variance of the noise in GNSS time series corrected from GRACE-derived loading displacements. And the average variance reduction is a bit more than 20% in up, 5% in north, and practically nothing in east. Let's finally look at the spatial correlation of the noise in GNSS time series. So on these plots, each blue cross represents the correlation coefficient between the noise in a pair of station position time series as a function of the distance between that pair of stations. And the red segments are average correlation coefficients per path of distance. These plots are for raw GNSS time series without GRACE corrections. And here are in light blue and purple the same plots, but for GNSS time series corrected from GRACE-derived loading displacements. And the red line on the right is the same as on the left, it's just shown again for comparison. So as could be expected from the previous slide, GRACE corrections do not change the nature of the structure, the spatial structure of the background noise very much in horizontal, but they, however, notably reduce the spatial correlation of the noise in GNSS time series in vertical. So let's now move to the summary and conclusions. We saw that the background noise in regularized GRACE solutions has a flicker behavior in average, that its geographical distribution follows that of the expected surface mass transport signal, and that this noise is highly correlated among different GRACE solutions, so that it is likely mostly real aperiodic surface mass transport signal. Then we saw that the loading deformation under this aperiodic surface mass transport observed by GRACE shows significant correlation with the GNSS station position time series, and that it explains about 20, or a bit more than 20% of the GNSS background noise in vertical, but only a few percent in horizontal. And that also contributes to the spatial correlation of the GNSS background noise in vertical. Finally, the remaining non-loading GNSS background noise is still partially spatially correlated, so that it must result from both spatially correlated and station-specific processes, which remain to be identified. So we're in the same situation as for the seasonal variation in GNSS time series. And the general message to the IGS here is that there remains work to do, first to get rid of the spurious periodic signals or all the systematic errors in our station position time series, and also to understand the remaining unexplained seasonal variations and background noise in the series. Thank you for your attention.
Thank you. Do we have any questions for Paul?
My first question is, in the slide you presented a different component, PSD on GNSS.
Which slide?
The east and north and up component on the PSD, which have some offset, or is that a signal different?
No, there are artificial offsets in the plots.
Oh, it's the offset.
Yeah, sorry, I forgot to mention that. Yeah.
This one.
Yeah.
I see. So the second question is how to get the east and north component from GRACE model.
GRACE gives you surface equivalent water height, surface mass variations.
Yes.
Then using the law of numbers theory or green function.
You take a derivative on the. So you just take the derivative from east and west.
Or you convert the load given by GRACE into displacements on deformation of the crust using the law of numbers theory.
Okay. Okay, I get it. Thank you.
I know there are a couple of other questions, I'm sorry, but we are